water table would go down. Did I dig it deep enough? Even though it's a deep well, I'm going to have to deepen it some more to make it a year-round well. This starts getting expensive. So you can see that we've got this water table now, and above it we've got a section of earth that no water. Sometimes when the water table's high, it'll be full of water, but other times when the water level is normal or low level, this area right below the surface is going to be dry. And those void spaces, instead of being full of water, are going to be full of air. And they're only going to be full of water when filtration's going on, when rainfall's hitting the surface, that water's making its way down to the water table, or as the water table rises, as it fills, it's going to use those pore spaces. But for the most part, we've got this zone of dry earth, and we call that the zone of aeration, because the pores are full of air. Now, if I were digging down, would I just kind of go from the zone of aeration into the water table, the zone of saturation? Would that just be a nice, boom, I'm there, I can see it instantly? Not going to happen that way. There's going to be kind of a transition zone. And as you start kind of approaching the water table, it's going to start getting wetter. And then finally, it'll get a little damper. You'll see a little bit of water. And then finally, you'll be into the zone of saturation and it'll be fully wet. So why do you get this little bit of a transition zone? It's what we call the capillary fringe. One of the properties of water is capillarity. Because there's a little surface tension associated with water, it can work its way up between the grains where there are little openings along the permeability. So some places it can work its way up a little higher, some places a little lower, but that zone of capillarity fringe is going to vary, but usually it's something like that. So you'll see this kind of fuzzy boundary between the aeration zone and the saturation zone. Water in the ground moves relatively slow. In most cases, we're talking maybe a few feet a day, most. Pretty slow. It's going to be much higher on a surface stream. And if you think about it, that makes sense. Because look at all the friction you've got trying to move that water along these tiny little pore throats, tiny little openings between the grains, and all that surface that's exposed means friction at every point. So it's going to be a pretty slower thing. Now, if I have groundwater that's moving along a big fracture, like here in this limestone, then it's more like an underground river. I've eliminated most of the friction because it's just one big crack that it's moving along. But if it's moving through a sandstone, it's going to take a little while. In Florida, there's a problem called the flying swimming pool problem. It's because of the groundwater. It's just like putting a boat in the lake. The boat floats because of buoyancy. Well, in Florida, where they have high water tables, if you want to put your swimming pool in, you're essentially putting it into a lake where the water is there, it just has a fair amount of earth associated with it. But if you were to dig out the hole to put the swimming pool in, you'd see that the hole filled with water all on its own very quickly because the water table was so high. You're trying to put your swimming pool into the water table. And in many cases, the only way you can keep it there is to weight it down. And you weight it down by keeping it full of water. Let's say something happens to the plaster of your swimming pool and you have to drain the pool to replaster the surface. Now you've got a problem You take the water out of your swimming pool, forget about it for a day or two, and all of a sudden you'll come back and your swimming pool will have popped out of the ground. It's floating on the water of the water table. So a few little extra problems with pool maintenance in Florida in a lot of places. Have you ever kind of noticed there are different wells in different parts of the country, different styles? If I go to New England, you know, one of the first things you kind of think about is the quaint New England inn, and they've got the well out in the front yard, and it's a well lined with stone, and it's got a little roof over it, and a bucket on a winch, and you lower the bucket down the well and pull the water out. Well, most of those wells were hand-dug wells, and the stone was added to keep the hole from collapsing. And for the most part, those wells, 15, maybe 30 feet deep at the most, depending on how hardy the soil was. And the bigger the well, generally the deeper it goes, because you need a bigger hole to stay open. But that was about the limit of being able to hand dig a well and line it with rock to keep it open like that. That worked in New England where you had a high water table. But what about Kansas? Do you ever see that kind of a well out in Kansas? No. There the water table's down a couple 100 feet at least. I don't know if I even want to crank open up the well that far every time, even if I could. Out in Kansas, what you see is the tripod with the windmill up on top, right? And it's running a pump, and it's pumping water, and the well is drilled, and it's lined with an iron pipe, and usually the iron pipe's about a 3-4 inch pipe, and that goes down 200 feet, and the pump is sucking the water up the iron pipe. Whole different deal. And the water table's just that much lower, so that, you've got to do that. All of those windmills that used to dot the whole middle part of the country, most of those windmills used to be made right here in Kalamazoo. And if you go over by the river, just kind of north of the downtown area, right along that stretch of river where Mackenzie's Bakery is and some of that over there, that's where most of the windmills were made, in that part of town. Of course, by the end of the 1800s, with the advent of electricity, you didn't need windmills so much. Once you had electricity on the farm, the electric pumps kind of took over. And there went the business. So things kind of changed in Kalamazoo. Well, we talk in terms of a couple different ways of having an aquifer. An aquifer is just a body that can hold water. It's rock with enough porosity and enough permeability. And it usually is confined by beds that are impermeable. In other words, they can't hold water. They act as seals to the aquifer. And that means that these would usually be things like shales or igneous rock or metamorphic rock or something with no permeability. So whenever I have an aquifer that is between a couple of these units, then I've got a confined aquifer. But if I have a bed, an aquifer that's just sitting there, where maybe there's a confining layer at the bottom, but the top is just open to the zone of variation and the surface, then I have an unconfined aquifer. Which would you rather have? Well, an unconfined aquifer is going to be closer to the surface, so I wouldn't have to dig as deep a well, so that would be good, save some money. But there's a problem. It also means that if water can infiltrate easily, so can contaminants, so can pollution. Now, out in the country, that may not be a big issue, but when you start getting in the city, the population goes up, the concentration of contaminants goes up, then it becomes a bigger problem. I put in a well at my house about 12 years ago in Battle Creek. And up until then, the rule had been you can just drill a well down here into the unconfined aquifer, about a 40-foot well, and you were okay. You'd meet state code. But of course, 2 weeks before I drilled my well, they changed the code, and all of a sudden, that wouldn't work anymore. You had to drill down past the first confining layer into the second aquifer that was a confined aquifer. The idea being the issue of pollution. So instead of a 40-foot well, I got to dig an 80-foot well. Yeah, twice the price. But I got a better well out of the deal. It's a safer well, and it's going to last longer. So, you know, it was a little annoying at the time, but at the same time, you get what you pay for sometimes. Sometimes you get a confining layer, an impermeable layer, and it just goes for a short distance. It's not widespread. And we get a lot of these around here because of the glacial deposition, where we just got a little layer of clay kind of laid down and then some more sands over that. So we see these around here on occasion. And this will keep the water from infiltrating past it. It acts as a kind of a floor and sets up what we call a perched aquifer. The area above it will hold water. And of course, toward the edges, well, can then get past that confining layer and get all the way down to the permanent main aquifer down below. So if I'm drilling this well and I come down here and I go, I got water, I'm all happy, I stop drilling my well. But then comes summer, and all of a sudden the water on this perched aquifer kind of shrinks, and all of a sudden I don't have a well. So what I would end up having to do is drill through that perched aquifer and tap into the main aquifer deeper down. So perched aquifers can give you kind of a little false hope sometimes, but they usually are limited in their supply and tend to be a little more susceptible to seasonal variations. Okay, true or false? The water table is very sharp, distinct surface between the zone of variation and the zone of saturation. Seconds. Okay. False, yeah. You gotta remember that capillary fringe there. It really is kind of a fuzzy zone. Okay? No, not the same surface at all. Okay. Well, here you can see some instances where the water table has been cut by a valley system, and look at the water kind of squirting out of these beds up here. Well, that's the water table. And the water table is just intersecting the side of this valley, so it's coming out as a spring running down the side of the valley onto the surface. So very typical. Now, sometimes it's just a matter of we have an impermeable layer with a permeable layer on it, so it's acting like a perched water table. Or maybe it's a sign of fractures, and this spring is just a fracture that's intersecting the surface, and we're draining the fracture system back there. So it may not be that there's just a single big aquifer there. It may be that it's just a localized system. You know, we think in terms of showers and baths as something we all do at home, no big deal. But you know, it was only really until about the 1880s or so that homes really had baths and showers. Pretty much before then, that was something that you would go to a hotel or a bathhouse, or previously to the baths in Rome, in order to do that. I mean, it was kind of a specialized type of a business. And in Bath, England, the Romans, when they occupied England, found this natural hot spring, and they built it into a set of baths, public baths, and they're still there. And that is what the town of Bath, England is built around. It was kind of the place in this wild outpost of Rome where you could actually get cleaned up for a little bit. Other thing, it was hot water. It was a hydrothermal spring. So it was hot water, not just cold, chilly, miserable water like everything else in England was. So how do you get water out in the desert? This idea of an oasis. Well, again, you're simply getting the water table above the surface of the land. And in this case, we've got this aquifer system that's coming down from the mountains, it's moving along, and we've got an anticline fold here, and the top of that anticline's been kind of chopped off a little bit, and it's sticking up here in the middle of the desert. So the water, as it seeps into this end of the aquifer up there in the mountains, the water's going to run through the system. It's going to fill up that aquifer, and the water level is going to rise to whatever level it is back here in the mountains in the aquifer. So that's going to help to bring the water to the surface. In this case, I've got that same aquifer. It's hitting a fault zone. The fault has offset some impermeable rock against that aquifer, and the water is just leaking up along the fault zone. So as it does that, it then collects on the surface, and you'll notice that we get a bunch of these oases now that are all kind of lined up. They're all just right along the fault zones. So as you might guess, in the Middle East, a lot of the original trade routes that meant you had to go from oasis to oasis to oasis were nothing more than following the old faults. Geologically, it was set up for them. Okay, what drives the natural flow of groundwater? What do you think it is? Okay, everybody in? All right. Looks like people like A. What is A? Pressure and gravity.
What did you eat?
Okay. Yeah, basically, that's a pretty good answer. Okay. I have an unconsolidated graph containing abundant pores, and they're well connected to one another. Okay, that would make a good what, because it would hold what kind of accessible water? Turn it on. Give you 25 seconds. A little breathing out first.
He said
Okay, couple more. Yeah. All right.
Let's go.
Ooh. G is a popular one. Okay, let's see. Well, we know it's going to be an aquifer, right? It's going to be able to hold water because it's got porosity and permeability. If it didn't have porosity and permeability, it would be an aquifer. It would be retarding the flow of the water. And it's going to hold a lot of water or a little bit of water. Well, it says it's got abundant pores. That makes it with a lot of available space to hold water. And it's well connected, so it's got good permeability. So I would say it's gonna be an aquifer with an abundant amount of water. Good aquifer.